Okay, fine. So functions are data. How is that actually going to help us reduce redundancy in our code? I think this will give a pretty compelling example, a pretty compact and compelling example of why this is a helpful thing to try, why treating functions as data can really help us. What I have in main are 4 vectors. I've got a vector of entirely zeros, a vector of non-negative even numbers, a vector of even numbers that include some negatives, and a vector of odd and even numbers where none of them are negative. So a mixture of various vectors of various characteristics. For each vector, I call this function print results. And the print results function calls these other functions to ask various questions, like, are all of the elements of the vector even? Are all of the elements positive? Are all of the elements 0? Is any element even? Is any element positive? And is any element 0? So I'll just run this to show the output that we expect to get. The program works correctly, but I would say it is the subject of quite a bit of duplication. Okay, so V0, for example, is all even because 0 is an even number. It is not all positive because positive numbers are not 0, so a positive number has to be 1 or greater. It is entirely 0. There is at least one even element, so any element is even. It's not true that any element is positive, and it is true that at least one element is 0. So we're asking all versus any for 3 different conditions, even, positive, and 0. V1, every element is even, so it's all even. It is not all positive because there's a 0 in there. It is not all 0 because there are elements that are non-zero. Any element is even because there's at least one even element. It is true that there is at least one positive element, and it's true that there's at least one 0 element. Okay, and then V2 is also all even. It's not all positive. It's not all 0. Any element is even. Any element is positive, and any element is 0. I think that's the same characterization as V1. And then V3 is not all even because there's an odd number in there. It is all positive. It's not all 0. Any number in it is even. There's at least one even number in it. And there's actually 2, 6, and 10. It's true that any element is positive. I mean, in fact, they're all positive. And it's not true that any element is equal to 0. Hopefully you get the idea. What I'm doing is calling these functions, and each function is asking a combination of either all versus any, and whether it's even, positive, or 0. So there actually are sort of 3 different conditions and 2 ways I could test them, all versus any. And we can already see that because of the weird mix and match way these functions are written, maybe there is going to be some redundancy. And there sure is. So here are my implementations of each function. One thing I guess I didn't make clear, the functions all return type bool, but by default, when a bool is printed, it gets coerced to an int, so it gets printed as 1 or 0. That's why we're seeing 1s and 0s instead of true or false. All right, so I've got my all even function. How does that work? Well, I iterate over my vector v, and then for each element x, I ask the question, is it true that this element isn't even? And recall that an element is even if the element modulo 2 is equal to 0. So if it's a multiple of 2, then it's even. In this case, if the element modulo 2 is non-zero, then it's not a multiple of 2. So if I find an element that is not a multiple of 2, then it's not true that the whole vector is even, so I return false. Okay, what about for asking if every element is positive? Okay, so an element is positive if it is 1 or greater. 0 is not a positive number. So I iterate over the vector. I ask the question at each step, is this element non-positive? Is it less than or equal to 0? If I find any element that isn't positive, then I return false. Okay, so what I'm really doing here is to ask if the whole vector is positive, I go looking for any case where an element isn't positive, and if I find such a thing, I return false. Okay, is the whole vector 0? I look at each element, I ask, is the element not equal to 0? Because if so, the whole vector isn't 0. And you can see, although the functions are short, all 3 of them are almost identical. The only thing that I see that's different is the inside of the loop, this condition. The condition really isn't... the condition is sort of independent of the way that I'm testing it. So that I'm iterating over the vector, and when I return false and when I return true. All 3 of all even, all positive, and all 0 have the same iteration logic and the same pattern of when they return false and true, but a different condition. And the condition is just a yes or no question. Okay, what about the any's? Okay, so to ask if any element is even, I iterate over the vector. I ask for each element, is this a multiple of 2? If the answer is yes, then I guess I found an even element, so I return true. If I get to the end and the answer was never yes, then I suppose that there isn't any even element of the vector. Notice that this is also pretty similar to what's happening in the functions above. Okay, and so then any positive. I iterate over the vector. I ask, is the element positive? Is it greater than 0? If so, then I return true. I found a positive element. Is any element 0? I iterate over the vector. I ask, is any element equal to 0? If so, then I return true. And again, the three any functions have a lot of similarities. The iteration logic and when I return true and false is exactly the same. The only thing that differs is that yes or no question. And also notice that between, let's say, any 0 and all 0, the only real difference between the two of them, besides the any versus all, in that condition, the difference is the condition is being negated in the all case, and it's being taken normally in the any case. If I ask, is the element equal to 0 in the any case, I'm going to ask the opposite. Is the element not equal to 0 in the all case? So between these 6 functions, there are a lot of similarities, but it's not really clear what I do to untangle them. Because I don't want to write 6 functions here, because the more conditions I add, every new condition, so I've got even, positive, and 0. What if I want to test if it's a prime number? Is every element a prime number? Is any element a prime number? What if I want to test if it's multiples of 7? Is every element a multiple of 7? Is any element a multiple of 7? You can see for every new condition I come up with, I have to write 2 functions, the all version and the any version. And that's going to be a lot of work. Similarly, if I make something besides all and any, for example, more than half or something like that, I now have to remake the function for more than half even, more than half positive, more than half 0. So the fact that I'm mixing and matching all and any and positive, even, or 0. I'm mixing and matching those. But if I bake those into functions like all positive and all 0 and any even, then the more conditions I add, the more complicated my code is getting, to a point where it becomes completely unmanageable. What I want to do in this video is decouple these functions. I would like to decouple the all versus any logic from the condition that I'm testing, 0, even, or positive. And that is my prompt. I want to condense them down into a generic all of or any of function, where I provide a condition to the function as an argument. Then I can just have a big collection of conditions, and I can have a collection all and any, and then I can just combine them as I see fit. I can mix and match when I use them. I don't have to mix and match when I write the functions. Okay, so how am I going to make that work? I think what I'm going to do is I'm going to write very basic functions for each condition. I'm just going to ask the question. You give me an int. Is this int even? Yes or no? So just, is it even? You give me an int x, and I want to ask the question, is x an even number? Well, it's an even number if it's a multiple of 2, which occurs if x modulo 2 is equal to 0. There's a very simple function that does one thing. The all even function sort of does 2 things. It has the condition about whether something is even or not, and it iterates over a vector testing if that condition holds for all things. It's 2 types of behavior mixed together. So because I've mixed them together, I have to write a separate function if I want a different mixture, if I want the any case instead of the all case. The is even function does just one job. Okay, what about is positive? Is positive? Well, a value is positive if it's greater than 0. Okay, and then finally, is the value 0? This one should be pretty easy. A number is 0 if it is 0. You can come by the office hours if you want to talk about that one further. Okay, I now have 3 basic condition functions. All they are is a condition. They just ask one yes or no question. Okay, so now what I want to do is I want to make functions that I can mix together. So I want to ask the question, using the is even condition, could you tell me if every element of the vector obeys this? Is every element of the vector even? And similarly, using the is even condition, can you tell me if any element of the vector meets that condition? I want to make a generic all of or any of function. So I'll say, okay, bool all of. And you give me a vector. I'll just steal the signature from down here. You give me a vector, and then you give me a condition. Okay, wait, what kind of condition? How do I pass in a condition? Oh, that's right. I have these functions that implement conditions. Notice how every condition function has the same basic signature. It takes an int and returns a bool. So if I want to provide the all of function a condition to test, I could just give it a function. So I take std function, and the function is going to return a bool and take an int. Remember from the previous video that when I use the std function type, what goes in the angle brackets is the condensed signature of the functions I'm working with. So I remove all the names. So I remove the name is even, I remove the name x. And so I get bool bracket int. That's how I boil it down to what I put in the std function angle brackets. Okay, so you pass in a condition to test, and you're now asking me, does this condition hold for every element of the vector? So I try it. I iterate over every element of the vector x, auto x in v. And I say, okay, for each element x, I'm going to evaluate the condition. I'm going to call the condition function on x. And if that equals false, And you could do this. There's a shorter way of doing this with a logical NOT operator. I get it. I evaluate the condition. If on any of the elements the condition comes out to false, then I know that it's not true that all of the elements of the vector obey the condition. So I return false. Contrast that to the, I'll bring up the all even function from below. Just to remind ourselves, this is the usual logic we see in the all functions. I iterate over the vector. I ask if the condition doesn't hold. This is asking if the number isn't even. And if that's the case, I return false. Here, when I want to ask if this abstract condition doesn't hold, then I would evaluate the condition function, this abstraction of some condition. And if it returns false, then the answer was no, so I return false. If I get to the end and I've never returned false, that means I guess the condition held for every element of the vector, so I return true. And there is my more generic all of function. And I guess while we're on the subject, let's write the any of function, which will also take an abstract condition, so just some function that returns yes or no. It will look at every element of the vector and it will ask the question, does the condition return true? I will use equals equals true to make this explicit. If I find any element where the condition returns true, then I return true. And if I get to the end and I haven't done that, then I return false. And so now I've got these functions, all of and any of, and they are completely decoupled from the conditions, even, positive, and 0. So I've untangled what I previously had 6 functions for into, well, it's 5 functions. But the advantage of this decoupling is now if I add a new condition, all I need is a new condition function. I don't need to rewrite both all and any. I found a way of decoupling the two things that each of these functions is doing. I'm now going to go through and just delete all of the old ones. Okay, but I'm not done. When I call my print results function, I have to, instead of having my all even function, which no longer exists, I have to call the all of function. So I call the all of function, and the condition I pass in is the is even function. So I say, is it true that every element of V is even? And the same thing here. So I call the all of function, I pass it V, and then I say, is it true that every element is positive? And then down here I call the all of function, and I give it the condition function for is 0. And here I call the any of function, and I give it the condition for is even. And you can see here I'm mixing and matching when I actually call the function. So whether I need a particular combination of the any versus all and one of the conditions just comes down to whether I choose to pass it in or not. So here's is positive, and then finally any of, and then I give it is 0. There we go. And we'll try running that. And it compiles, and we stare at the output, and hopefully you can verify to yourself that the output is identical. So I've decoupled the two different things that were happening in my functions to create a sequence of functions that I can now mix and match. This is great, because it means if I add any new conditions, all I need is a new condition function, one clean extra thing. If I add any new quantifiers, if I want to do something other than just all or any, so for example, if I want to do at least half, or at least 2, I just write one more of these functions. I don't have to worry about making all possible combinations of quantifiers and conditions, because I can always mix and match through the use of these function objects, a technique out of functional programming, when I need to do the evaluation, when I actually call the all of function. All right, so there's an example of decoupling, I think, in a pretty isolated sense. This is what we want to get at with our earlier example of those cases where we're pairing up elements of lists, and we're on our way there. Just before the video ends, I want to talk about how we can extrapolate this logic further. So eventually you might say, well, hey, I don't just want to do all of on vectors of ints. I might want to do all of on vectors of anything, or go even further and do all of on collections of whatever. Anything I can iterate over with a for each loop, I should be able to do the all of quantifier on. I'll take us one step into that process. So here I've written a templated version of the all of function. It's a little bit different. I mean, I haven't included curly brackets, and I've called it condition function to make it more clear, but I have a templated version that takes a vector of type t. And that means that the condition function has to take an element of type t and return bool. Everything else is pretty much the same. And here's any of, and it takes a vector of t and a condition function that takes t and returns bool and does the similar thing to what we saw a minute ago. And now I've got some condition functions. Notice that my condition functions aren't templated because I've got special conditions for int elements. I've got other conditions for string elements. So for example, we decide whether the entire string is lowercase. You give me a string, I will go through it and ask the question, oops, I should probably call std is lower over there, I should go through and just ask if every character is lowercase. So I have condition functions for strings and for ints, and I can just mix and match them with these quantified all of and any of functions. In this case, I'm using explicit template instantiation just to make that absolutely clear what I'm trying to do here. And we'll just try compiling and running this. There we go, and it compiles. And so I've got these various vectors. So I've got vi1 and vi2. vi1 is all positive, but it does contain odd numbers. And we can see, okay, so vi1 is not all even. It is all positive. There is at least one even element. There is at least one positive element. vi2 contains both negative and positive numbers, but they're both even. So it's all even, not all positive. It contains at least one even number and at least one positive number. I now have two vectors of strings. One of them contains strings that are entirely lowercase. One of them contains strings that where none of them are lowercase, and here we can say that, and also an element is considered to be short if it's less than 6 characters. Yeah. So here there is at least one short element in VS1. Every element of VS2 is short, and sure enough, VS2 is entirely short. VS1 isn't. VS1 is not all lowercase. VS2 is. They both contain at least one short element. VS1 does not contain at least one lowercase element, and so I was able to generalize this. I could generalize it further to not just take vectors of anything, but a collection of anything, not just a vector, but a list or a set or something, because you can iterate over lists and sets, so why not generalize all of to that? There is an all function in the standard library that does exactly that. It iterates over basically anything that you can give it that can be iterated over, and it takes a condition that returns bool. And so I think I've shown that we can use these function objects as a way to decouple. We can take that a lot further, and we'll do that in the next couple of videos. After that, we'll begin talking about whether there's a less clunky way of writing these conditions. Sure, a 3-line function's not so bad, but maybe if I only need the condition once, I shouldn't have to put it up here in the global scope. Maybe I should be allowed to make up functions just like I make up any other variable in the middle of other code. And we're getting there too.